6.7, our last concept in chapter 6 in dealing with different types of probability distributions and random variables. And the one that we're going to focus on in 6.7 is called a geometric distribution. A geometric distribution and a binomial distribution are very similar, meaning they actually have 3 of the 4 conditions that are exactly the same. The first one that's exactly the same is it's binary also. A geometric distribution will either have 2 options. Either it's a success or a failure. It also needs to be independent. So one trial can't affect the other. Okay. If you're sampling without replacement, then you can use that 10% rule. Here's where it changes. Okay. Instead of it being n, the number of trials is fixed, a geometric distribution is one where you go and you count until you get the first success that you're looking for. So when I think of the difference between a binomial and a geometric, I can think about rolling a pair of dice and looking at whether or not you get doubles or not doubles. Okay? So for instance, when rolling a pair of dice, just to let you know, the probability of doubles is 1 out of 6. Because there's 6 sets of doubles out of 36, or 1 out of 36. Or sorry, not 1 out of 36, 1 out of 6. Okay? So when I think about the trials part, okay, in a geometric, you're going to roll the dice and count how many times you have to roll it until you get your first set of doubles. In a binomial distribution, that's going to be fixed, meaning you might say you're going to roll the dice 10 times and count how many doubles you get in 10 rolls. Okay. So with the geometric, you can roll for a very long time. Okay. Probability of success, the last one is exactly the same. So for our acronym here, it just changes from bins to bits. So understanding that a geometric, you keep on going until you get that first success. Sometimes I think of the game Monopoly. Okay? If you think about the game Monopoly, okay, if you go to jail, what's one way with the dice that you can get out of jail? Yeah, you roll the doubles. And you sit in jail until you roll doubles. Of course, in Monopoly, I think after, 3 turns, you can pay $50 and get out of jail. It's been a while since I played Monopoly. But in a way, that's a geometric distribution. You keep on rolling until you get a 6. Or another board game. How many of you remember playing Sorry? Oh, yeah. What do you have to do in order to be able to start?
Roll 1.
It's not a 1 or you don't roll, but you draw a card, but it's a 1 or a 2, right? Yeah. So you have like a deck of cards that have the numbers like 1 through 12 on them, and you keep on drawing until you get a 1 or a 2. Okay. Now that one we have to worry about the probability of success, because since you're not putting the cards back, the probability does change. But the concept and the thought process, you go until you get your first success, is what the geometric process is all about. Okay? So when we take a look at a geometric distribution, if we define the number of trials as y, okay? In a geometric distribution, when you start to take a look at the number of trials you have to do, unlike the binomial distribution, you're gonna actually start not at 0, but at 1, and you're gonna go and calculate on technically forever. In a binomial distribution, if I use x and p of x here, you start at 0 and go 1, and you stop at n. That's the difference between the two. So how do you calculate out the probabilities? Okay. We'll show you how to do it by hand, and we'll show you how to use the calculator. By hand, I actually find the geometric probabilities by hand sometimes actually faster than doing the calculator one, depending on which ones you're given. Okay? If you think about how a geometric distribution works, we look at how this is set up. K is where you want your first success. Okay. Remember that 1 minus P is the probability of failure, and P is the probability of success. So if you think about how this formula is set up, the probability that your first success occurs on a specific number, well, you have to fail one less time than where you want your first success to occur. So you're going to fail, K minus 1 times. Then you're going to times it by the probability of success. For instance, if my probability, or if I want to say, I want to get doubles on exactly the third roll. So this would say doubles on exactly the third roll. What has to happen is I have to fail. Probability of failure would be 5, 6, and I have to fail 2 times. I have to fail on the first roll, and I have to fail on the second roll. So I take that to the second power. Then on the third roll, I succeed. So if I want to succeed on the third roll, what has to happen on the first roll? Fail. What has to happen on the second roll? Fail. So if 5, 6 is the probability of failing, that has to happen twice. So it'd be 5, 6 times 5, 6, or 5, 6 to the second power, and then I succeed 1, 6. So like if I have probability, say if I want it to happen on exactly the 6th roll, I would have to fail 5 times and then succeed on the 6th roll. So lots of times I actually find if it's an exact problem, it's sometimes a little bit easier to calculate it out by hand. Now here's the nice thing. Your calculator does them, or does these calculations also. Just like binomial PDF and binomial CDF, on your calculator you have these two functions. Geometric PDF and geometric CDF. PDF, just like with the binomial, goes with the equals. The CDF cumulative goes with the less than or equal to. Now notice in geometric, you actually only have 2 values. Okay? You have the probability of success, and when, and K, when do you want that success to occur? You don't have N, because N doesn't exist in a geometric situation, because you could technically keep on rolling and never get doubles. That would just be a bummer. Okay? Alright, so we'll show you how to do where these are located on your calculator. Just to let you know, if you go second bars, and you go to the very bottom, you'll see geometric PDF and geometric CDF. So like for instance, if I want to do this one exactly 6, just to show you, what I could do is go geometric PDF. My probability of success is 1, 6. So I can type it as a fraction. And I want the first success to occur on the 6th roll. That would be my probability. Just to show you, it's the same answer as doing it by hand. The other way I could have done it was 5 divided by 6. This one I actually have to put in parentheses because I need to raise that fraction to the 5th power. Then I need to times that by 1 divided by 6. Notice how I get the same answer. So using the formula by hand or the calculator is just fine. Just note, if you use the calculator, please make sure you know what P is and what K is. Now the other last thing about geometrics that will be important, okay, is you can actually calculate out the mean or expected value of a geometric random variable, okay, which is basically what's the average number of times do you need to do something to get your first success. It's a very simple and easy formula to calculate out. It's simply 1 divided by the probability of success. If you think about it, rolling doubles, 1 divided by 1/6 is actually 6. You would expect, on average, it would take you 6 rolls to get doubles. Alright. Ready to look at some examples? Or at least one example. It's our last page of Chapter 6 notes. Woohoo! One of my favorite problems.
Breakfast cereal.
Breakfast cereal. Because it reminds me of childhood. So, in this example it says, selected boxes of breakfast cereal contain a prize. Remember when you were a kid and you go down the grocery aisle with your parents, and maybe you still do, and you probably don't ride in the cart anymore. Did you ever pick cereals because of the prize? What was the prize that you liked? The rings. Ooh.
What?
Some cereals would have rings.
We used to have like light up spoons.
Light up spoons?
I still have.
You still have your light up spoon?
Yeah, we have a lot of them.
You know, I know some cereals would have race cars. I know they don't do prizes as much as they used to. For me personally, I remember always wanting the little plastic submarine that when you put baking soda in it and you put it in the bathtub underwater, the baking soda would react with the water and it would shoot itself across the bathtub.
Perfect.
It's pretty cool.
So easy.
So, anyway,
So they had fun.
according to this problem, it says, suppose that 20% of the boxes contain the prize and the other 80% contain the message, sorry, try again. A consumer determined to find a prize decides to continue to buy boxes of cereal until a prize is found. Consider the random variable x, where x is the number of boxes purchased until a prize is found. Ooh, found and determined to get a prize. Show that x is a geometric random variable. So we're going to run through our conditions. Is it binary? Yes. Either you get the prize or you don't. Is it independent? Does getting a prize in one box impact you getting the prize in the next box? No. So we would consider this independent, so we would say yes. Okay. So getting a prize in one box does not impact the chances of getting a prize in a second box.
Is that because there's an infinite amount of boxes?
You can think about, there's so many, yeah, you can
And
think
that's
about
why
it that there's, the number of boxes probably produced is very, very big, that it really doesn't impact because you're basically sampling without, even though you're sampling without replacement, you can think of, all right, if we're General Mills, how many boxes of Cheerios do you think they make on a daily basis?
A lot.
Yeah, probably what, 100,000? Okay? So if 20% of them have prizes in them and you take one box away, does it change the probability that much?
No, so if it's like a smaller number, would it then change?
Then you'd be worried about it.
Okay.
Yeah. And we can even note that here, since our population is greater than or equal to 10 times our sample. And that's basically the biggest key. I mean, our population is going to be really big. And I know we're going to go until we get our first success. Well, we'll see later on, the average number of times it should take us is, I believe, 5, but we'll calculate that out a little bit later.
Okay.
All right, so 3. Yep. Now we're talking about trials. Do we go until we get our first success?
Yes.
Yes. So we keep buying boxes until our first success. Ooh. I think I can actually squeeze it here. Success. What's the probability of success in this case?
20.
Yeah, 20%. So the probability of success, P of x equals 0.20. All right, part B. What a surprise. Just talking about what is the mean of x. Well, it's simply going to be 1 divided by p. So 1 divided by 0.2 is 5. So we would expect to have to buy 5 boxes on average to get a prize. So if you did it on the first box, hey, you did better than average. You even did it in 3 boxes. You did better than average. Five boxes of cereal. I hope you like the cereal. We can talk about the best cereals out there. Alright, so C says, what's the probability that at most 2 boxes must be purchased? So, looking at what's the probability that X is less than or equal to 2. I'm actually going to calculate this out the long way, or I should say the by hand and by calculator. I kind of hesitate with saying long way because this one doesn't take very long. Less than or equal to 2 is the same thing as saying I get it when. I get it on the second box and the first box. Well, what's the probability that I actually get it on the first box? 0.2. Okay. What's the probability that I get it exactly on the second box? What must happen on the first box? I must fail and then succeed. Well, we can probably do this math by hand, can't we? What's 8 times 2? 16, 2 decimal places, 0.16. So what's 0.2 plus 0.16? 0.36. So, now for you, those that like the calculator, oh, I hate it when just gonna move that. If I wanted to use my calculator, I could go geometric, CDF, my probability of success is 0.2. I want the number of successes to be 2 or less. So that's my K. So if I'm using my calculator, I could go second bars. You can scroll to the bottom. I find it's faster just hitting the up arrow because it'll take you to the bottom of the menu. CDF, 0.2, comma 2. And this will find it for you also. Sometimes I find calculating them out by hand a little bit faster and a little bit easier.
Wait, why don't we have to do that thing where like, we put it to the power?
Well, you didn't have to put it to the power because the value was 2, so I only had 1 failure and 1 success. If this was like 7, then this would be, yeah, or to the 6th power, yeah. So here on D, I'll show it. This is where you might have to take it to the power.
Okay.
D says, what is the probability that exactly 4 boxes must be purchased? So, in this case, I'm looking at x to equal 4. So if I'm thinking about this one by hand, okay, what I can do is I could go, well, I have to fail how many times? 3. And then succeed. So 0.8 to the 3rd power times 0.2, 0.1024. Now, I could have used geometric PDF. My probability of success is 2. I want it on exactly 4 times. Just to show you that I do get the same answer. Second bars, geometric PDF, 0.2, comma 4, 0.1024. All right, last one. What's the probability that more than 4 boxes must be purchased? So I'm looking at, well, what's the probability that x is greater than 4? So I'd have to calculate out 4, 5, 6, 7, 8, 9, 10, all the way to infinity. Can I do that straightforward? No, I'd be calculating on forever. So, is there another way that I could think about these? What should all the probabilities add up to? 1. So, if I do the complement 1 minus, what would be the complement of greater than 4? Less than or equal to, the question is, do you include 4 or not? You actually do, because it says greater than 4, so that would actually be 5, 6, 7, 8, 9, 10, 11, all the way to infinity. So I want to figure out 4 or less. So, on this one I could do geometric CDF. Point 2, comma 4. So again, here's P, here's K. Now this is CDF, not PDF, so I can't take the answer from previous one to get it. So, back to my calculator. 1 minus, second bars, geometric CDF, 0.2 comma 4, 0.4096.
How would you do that one by hand? Or
Well,
would you not?
I could. What I would have to do is I'd have to calculate out this one, so I'd have to do exactly 1 plus exactly 2 plus
So it would
exactly
just be too long to do it.
3 and exactly 4. It's not terrible. I mean, this is, I know, 0.2 and this was 0.16. I could do this one here,
We already
which
know.
would be 0.128, I believe.
We already knew 4.
Yeah, and we know 4 is 0.1024. I could add those up and subtract from 1.
Okay.
That one's not terrible, but this is where the this is where the calculator is really nice.
Did we do the 1 minus? Did you do 1 minus and then the geometric on
Yep.
the calculator? Yeah. Okay.
Yes, I did. Yep. All right. So